Energy is the ability to do work. There are two main types of energy. One is kinetic energy, which is energy of motion. And the second type is potential energy, which is energy that is stored. It could be stored due to height difference. It could be stored because there's an elastic storage or a chemical storage. Heat is not energy. It is a transfer of energy. By definition, heat flows from hot to cold. Temperature is not heat, but it is proportional to the average kinetic energy. So if we rewrite this, temperature is proportional to kinetic energy average. And kinetic energy is the motion of all particles. So the higher the temperature, the higher the average kinetic energy. But in general, if the object is heavier, it will move slower because kinetic energy is equal to 1/2 mass times velocity squared. So if you notice, mass and velocity are not directly related but inversely related. Thermal energy is the total kinetic energy, and it depends on the amount of substance. So if the classroom is at 100 degrees Celsius and the outside is at 0 degrees Celsius, there is more thermal energy outside than inside the classroom because in general there are more particles outside, or more atoms, molecules, compounds outside than there is inside the classroom. Energy can be transferred three ways: conduction, convection, and radiation. The first two, you need a medium. A medium is there must be particles present. If there is no particles present, atoms, ions, compounds, or molecules, conduction and convection will not occur. Radiation, you can have a medium or no medium is necessary. Conduction occurs because molecules bump into each other, so you need to have some sort of contact. Stove heats up an iron pan. When you touch the iron pan, there is a contact between the molecules or the atoms in the iron pan to your hand. Convection occurs because there's a difference in density. In the West Coast, we have warm winters and cool summers due to convection current. In the wintertime, the ground is warmer, and what it does is it heats up the air particles right above. So when we heat up the air particles, the density of the warm air is going to be less than the density of the cold air that is above. So what happens is the warm air rises and the cold air sinks. The warm air is blown into the ocean. In the ocean, we have water, and we learn water has a high heat capacity, which is 4.186 joules per gram degree Celsius, which means for 1 gram of water, it could change the temperature 1 degree Celsius by either releasing 4.186 joules of energy or gaining or absorbing 4.186 joules of energy. So the warm air goes to the ocean, warms up the water, and is blown back in to land. And again, the cycle repeats. The ground will warm it up again, the warm air rises, and then it's blown out into the ocean. In the summertime, it goes the opposite way. Radiation, we stated, does not need a medium to travel. Example of that is the sun heats up Earth. The rays travel through space, and in general, space has very little or no particle. Here we have two flasks. The system is the flask itself. Anything outside of the system is going to be known as the surrounding. When heat escapes, that means heat leaves, this is an exothermic reaction, which gives a negative value. When the heat enters the system, this is called an endothermic reaction, and it absorbs energy, and it is positive. There are three types of system. The first one is an open system. The second type is a closed system. And the third type is an isolated system. An isolated system, nothing is going to enter or leave. So there is no exchange. So no exchange with the surrounding. There is no exchange of mass or energy. A closed system allows heat to be transferred. So that means the lid is sealed, but the glass itself will let energy in and out. So if this was a flask of water, in a closed system, this water level will never change because it is closed. Nothing can enter or leave. There's no mass exchange. He can leave or enter. If it's an open system, it allows energy and mass to both move. So mass can enter or leave, and heat can enter or leave. So in this situation, the water level will in general not stay at constant. It would either be higher or lower depending on the surrounding. Internal energy of the system is the total kinetic energy of all the particles. We could calculate the internal energy delta U or delta E of a system using the following equation, where delta U is the internal energy, Q is the heat that is transferred in or out, and W is the work done by the system or on the system. So you need to memorize the sign convention. Heat transfer, which is Q at this point. Later on, it will be delta H, which is enthalpy. The sign for positive Q is endothermic. Heat is absorbed. If it's a negative Q, it's exothermic and heat is released. For work, it's a negative sign if the system does work or work is done on the surrounding. Either or. If it's positive, if the surrounding does work on the system or work is done on the system by the surrounding. Work can also be defined as pressure times the change in volume. So if I write this in symbol form, is P delta V. And we remember triangle here always means V final minus V initial. We also need to note that the conversion factor 1 atm liter is equal to 101.3 joules. That means if we are using PV equals nRT, the R is no longer 0.08206. If you use that, you must convert it by using 101.3 joules. The first law of thermodynamics states that energy is conserved. It just changes form. It could go from stored energy to kinetic energy. It could go to spring energy, sound energy. However, the total energy of the system and the surroundings should be constant. The second law of thermodynamics states that entropy of the universe is constant. So if I have the entropy of the universe, it is equal to the system plus the surrounding. Remember, entropy means chaos or randomness. We also know that heat flows from hot to cold. So the entropy, which is symbol S, of a gas is going to be greater than the liquid, than the solid, because gas particles are spread out. They could go in random direction more than a solid particles which are held together in place. Zeroth law of thermodynamics states, if I have three objects labeled A, B, C, if A is in thermal equilibrium with B, B is in thermal equilibrium with C, then A and C are in thermal equilibrium. So what does equilibrium mean? Equilibrium means that the number is not the same. It means that the rate of exchange is the same. So even once it reaches equilibrium, its rate of exchange will still change at the same rate. So for example, if I have A and this was at 50 degrees Celsius and B was at 0 degrees Celsius, according to the second law of thermodynamics, heat will flow from 50 degrees Celsius, which is A, to B, because it flows from hot to cold. So what it's going to do is initially A is going to release more heat, B is just going to release very little. Even though A is at a higher temperature, B will actually return a little of the heat. Eventually, A and B will be at thermal equilibrium. That means the exchange rates will be the same, and the temperature will no longer be 50 degrees. Their temperature will be the same at the end. So if B and C are the same thing, and they are in thermal equilibrium, then A and C will also be in thermal equilibrium. At the end, the rate of exchange is the same as well as the temperature. You could think of the zeroth law as the distribution principle that you learned in math class. So in the following problems, we're going to calculate delta U. It says the system absorbs 85 kilojoules of heat from the surrounding. Since it's absorbing, we know this is an endothermic process. So we know this is going to be a positive, and it is heat, so we know this is going to be Q. From the surrounding while doing 29 kilojoules of work on the surrounding. So we know this is W. Since the system is doing the work, this is going to be a negative. So delta U is equal to Q plus W. Q is a positive 85 kilojoules plus work, which is negative, which equals 56 kilojoules. And if you line up the decimal, the least precise position is the ones place. Pause the video, try B on your own, and then check your answer. Here we have 1.5 kilojoules heat is transferred into the system. Since heat is transferred into the system, that means this is positive Q. It is being absorbed. While the system does 657 joules of work on the surrounding. So that means the system is doing the work, so that's a negative. So delta U is equal to Q plus W. This is equal to 1.50 kilojoules plus a negative 657 joules. We have to be in like units, so you either convert the kilojoules to joules or the joules to kilojoules. I'm going to convert joules to kilojoules. There's 1,000 joules in 1 kilojoule. And if you do the math correctly, 0.843 kilojoules. So if you line up the decimal, it will be 0.084 kilojoules, because this will be 1.50 kilojoules. The other one will be 0.657. Least precise is right here, 2 places after the decimal. Pause the video, try C and D on your own, and then check your answers. For C, we have a system that releases 57.5 kilojoules of heat. So we know this is Q. And since it's releasing, this is an exothermic reaction, so that's going to be negative. While the surrounding is doing 13.5 kilojoules of work on the system. Since the surrounding is doing the work, this is going to be positive. So delta U is equal to Q plus W. This is equal to negative 57.5 kilojoules plus a positive 13.5 kilojoules. This is equal to negative 44.0 kilojoules. You need to line up the decimal. 1 place after the decimal is the least precise position. For D, a system releases 125 kilojoules of heat. So we know this is our Q. Since it releases, this is a negative 125 kilojoules or exothermic, while 104 kilojoules of work is done on the system. Since it's done on the system, this is going to be a positive work. So delta U is equal to Q plus W. This is equal to a negative 125 kilojoules plus a positive 104 kilojoules, which equals negative 21 kilojoules. The least precise position is the ones place, so it's 21. This problem is a 2-step problem, so we need to find delta U for each one and then add it together. In step 1, it absorbs, so that means Q here is going to be positive. It's an endothermic. While 35 joules of work is done on it, so that means this is positive because the surrounding is doing the work. For step 1, delta U again is going to be Q plus W. Q here is positive 73 joules plus work, which is 35 joules positive. This is equal to 108 joules. In step 2, the system absorbs, so that means it's an endothermic process while performing 72. So that means that the system is doing the work, so this is a negative. So in step 2, this is delta U is equal to Q plus W. This is going to be 35 joules plus a minus 72 joules, which equals to negative 37 joules. So the delta U, or the internal energy for this system, is going to be 71 joules. Line up the decimal. In this one, we have a volume of an ideal gas is decreased from 5 to 5 milliliters. So this is our initial volume. This is our final volume at a constant pressure of 2 atm. Calculate the work. Work is equal to P delta V. Pressure is 2 atms. Delta V is V final minus V initial. This is in liters, this is in milliliters, so we need to convert. So my final is 5.0 milliliter. I need to convert that into liters using dimensional analysis. Minus 5.0 liters. This is equal to 9.99 atm liters. We want to be in joules, so we're going to convert. We know that 1 atm liter is equal to 101.3 joules. This equals 1,011,987 joules. It has 2 sig figs. So 1, 2, I look 1 to the right, it stays. So 1.0 times 10 to the third joules. The answer is positive because the work is being done on the system. How do you know? The volume decreased. To decrease the volume of a system, something on the outside must do work on it.